Hey guys, welcome to Term 2's physics lessons. We're looking at work, energy, and power this term, and every one of us performs work each and every day. And the concept of work in physics has a specific meaning, much like the concept of weight in physics. It means the gravitational pull on the matter that exists in us towards the earth, right? Which is very different to what everybody else uses weight as in the real life. So in this unit, we're going to discuss how to determine work done when forces act on objects. We're going to then look at when a net force acts on an object, its velocity increases or decreases, and the object therefore gains or loses kinetic energy. If the velocity increases, the kinetic energy will increase. If the velocity decreases, then the kinetic energy will decrease. This relationship between the change in kinetic energy of the work done on the object is known as our work-energy theorem. We will use this theorem to understand the energy transferred and the motion of objects. In this unit, we introduce also the concept of power, and we apply this concept to familiar, everyday situations such as pumping water from a borehole. So, to start us off, we're going to look at work and energy. In reality, work is a task or chores you have to complete, right? Very boring. We don't like those things. Washing dishes, all those types of things. Actually, even going to work. In physics, however, work is the energy that has been transferred by the force. It's a scalar vector, okay? But what is energy? Well, energy is the ability to do work. So if we look at work, it tells us it's the energy transferred by a force, which means I need to apply a force in this direction to carry this, whatever it is, looks like a sack of something, on this trolley. I have to apply a force in that direction to be able to get this item to move. If this item moves, then I have done work. So work is done when a force acts on an object and it causes it to move in the direction parallel to the force. Again, we cannot do any work on anything if we haven't made the object move. And that movement has to be specific. It has to be in the direction that is parallel to the force. So my force is to the right. What happens if my movement is up? Have I done work? Has there been work done on this object? Well, that's what we're going to look at. So, to work or not to work. The direction of the applied force, I as an individual am applying a force to the box. Which direction am I applying a force to the box? I'm not pushing the box forward. I'm walking forward, but my hands are not pushing the box forward. What ended up happening is I had the box here on the floor and it had to move up. So the direction of my applied force is up and my direction of motion is to the right. So this man applies an upward force on the box when raising it from the ground to his chest height. Work is done because the force is applied in the same direction that the box moves. But this man walks from left to right while holding the box at chest height. He does no more work on the box. The force he used to support the box acts in a different direction than in which the box is moving. So the box is moving to the right. The force in which work is done on the box is up. Therefore, there is no work being done in this example. Let's look at these examples. We have a lady, she is pushing this box along the floor. The force of direction is parallel to the direction of motion, and because these two are in the same direction, she is doing work. So if we look at this girl carrying a backpack, she's put the backpack up onto her back, so the force that was applied to that backpack is up, and she's moving and she's walking to the right. So has she done any work? No, she hasn't done any work with that backpack in moving in the direction of moving right. If we look at her bending her knees and picking up a bag, well done. She's got to bend her knees and not bend her back down. So she bends her knees and she lifts the bag. The bag moves in which direction? It moves up. The motion in which the bag is moving is also up. Therefore, work is being done. And then over here, she's lifted that bag, but now that bag, the force that she's applying to the bag is up, and the motion of direction that she's going in is to the right. So is she doing any work on that? No, she isn't doing any work. This takes us to our lovely definition for our work and energy. The work done by a force acting on an object must move a certain distance for work to be done on that object. Now, that's easy enough if we're working left to right. But what happens if we start applying a force at an angle? This is when we need to calculate our forces, our components of this force, right? So we call it our vertical and horizontal component. Our vertical component would be going up like that for our force, that's our vertical component. And here we have our, or it's perpendicular if you want to remember to call it that. And here we have our parallel component, which ends up being our horizontal component. How do we determine what this is? Well, if we had to make this a right angle triangle, just to remind you, this is my hypotenuse, this is my F, and this is my adjacent. So if I wanted to write this in terms of a cos, I can sit there and write cos theta is equal to adjacent over hypotenuse, right? Adjacent, which ends up being my parallel component, over my hypotenuse, which is my force vector. That's the force at which I'm applying, right? And now I want to know what my parallel component is. All I do is I make it the subject of the formula. It's dividing on this side. It moves up here and it starts to times with the F cos theta. And there we have the equation. And now I've written all over that equation. There we have the equation that we are required to use for the force that is being applied that is parallel to the motion of the box. So if we've got an angle, remember we have that vector and we have that vector. That allows this resultant to exist, right? So this is the force that we need to use that is parallel to that box. So here it says F and D will be absolute positive values. The direction of D will be a positive unit. It'll be 5 meters or 3 meters or 10 meters, okay? The force that we're applying is also going to be an absolute positive value. If it's in the direction of the movement, it's going to be positive. Theta is measured between the displacement and the relative force in an anti-clockwise direction. So we're moving this way. This is my distance, and in this direction, that's the angle that it makes with that. So look at these boxes at the bottom here. If my distance moved is in the same direction as my force, the angle theta that it makes between the D and the F is going to be 0. If my force is opposite the direction of my motion, the angle, let me get my little black pen out here, my angle goes up like this in an anti-clockwise direction, and that ends up being 180 degrees. Here, if my force is up while my direction of my box is to the right, I know that this is going to be 90 degrees then. And then over here, if I have my force, which is in the same direction as my distance, there is a 0 degree difference between these two lines. And over here, as my force is at an angle to the direction of my box moving, I end up getting whatever angle that is. So in this case, it's 45 degrees as stipulated, but it's not necessarily going to be 45 degrees all the time. It could be 30 degrees or 50 degrees. This force can be up that way, it can be this way, it can be in ever which way. And you've got to figure out what that theta is according to this line, the direction of your motion, and the applied force. Okay, so to allow for us to always understand that work is not just force times distance, because this force might not necessarily be in the same direction as the movement that the box is going. So if this force is at an angle other than the direction of what the box is going, we need to apply that cos theta to it. Okay, so your work now is equal to the force over the change in distance times your cos theta, whatever your angle is between this d and the force. So how do we know if we've got positive work and we've got negative work? Well, positive work means that my work value is greater than 0, so I get a positive answer. Negative work is if my work calculation gives me a negative answer, and that ends up giving me a negative work. Now, if I'm going in the same direction, there is no change in this. I'm going to say cos 0 degrees. And if I plug that into my calculator, I'm going to get an answer of 1. If I plug in cos 180 degrees, I'm going to get an answer of -1. If I plug in 90 degrees, cos 90 degrees, I'm going to get an answer of 0. Here, again, cos 0 degrees, we go back to the first one, that gives me an answer of 1. And cos 45 degrees, in this instance, if you plug it into your calculator, is root 2 over 2. How does that help me understand if I'm going to have positive or negative work? Well, look at your equation. Work is equal to your force times the change in distance, cos theta. This is always a positive value. That is always a positive value in this equation. This item changes your answer to tell you if you're going to have a positive work or a negative work. So if we take cos theta and we substitute 1 by it, let's go plug the 1 in over here. Let's put a 1 over here. We're going to have 1 times any of this, which means it's still going to be that. 1 times anything still stays that anything, right? If I times it by -1, all of that is going to change its sign. So if this was 20 and I times it by 1, I'm still going to get 20. If I times it by -1, I'm then going to get -20. If I times it by 0, I'm going to get 0. So if I want to calculate the work done, if I wanted to find out the work done here, I'm going to times it by 1, which means I'm going to get a positive work done. If I'm looking at timesing it by -1, I'm getting negative work done. Multiplying it by a 0, there is no work being done. Multiplying it by a 1 is a positive work. And multiplying it by root 2 over 2 doesn't matter. It's a positive sign. You will still have positive work being done. Example 1 of figure 1 and 2. We don't have the figures here. I'm going to draw those figures out for you. It shows a 2 kilogram block. And determine the total work done on the block when it is pulled horizontally by a 2 Newton force over a distance of 10 meters on a frictionless surface. And for number 2, it's carried a distance of 10 meters at a constant velocity by one person. So let's draw this little item. Item number 1, we end up having a block. It's pulled by an applied force across a horizontal surface, and it moves 10 meters. And item 2, let's draw our little stick man here. He is going to pick up our box, right? And once he's picked up our box, he lifts it up and he has it in his lovely little hands. Sorry, it's just fighting with me at this point in time. In his little hands, and then he moves 10 meters to the right. So, how are we going to calculate each one? Let's go. Number one, we end up having it's pulled over a horizontal surface by 2 newtons. So let's apply our work equation. Work is equal to the force times the change in distance times cos theta. Is the direction of my force in the same direction of my motion? In this case, yes, the direction of my force is in the same direction of my motion. Therefore, what do we know? Theta is equal to 0 degrees. There's no angle between my force and my direction of my distance. So I can go substitute that in. My force is 2 newtons, times it by the distance, which is 10, times it by cos 0 degrees, which ends up being 1. So this whole answer becomes 20 newtons. Number 2, it tells us it's carried a distance of 10 meters at a constant velocity by a person. So this person has lifted it up first and then is carrying it. Their applied force is in this direction, and we haven't been given that applied force. So my work is equal to my applied force times my distance, which is 10, and times that by cos theta. Now, what is theta in this instance? If my force is acting up and I'm moving my box in the right-hand direction, that means I've got an angle of 90 degrees between my force and the movement of the object. So cos 90 degrees ends up giving you a value of 0. And anything that is multiplied by 0 will still be 0. Sorry, it's not newtons. The unit in which we measure work is joules. It's the amount of energy, and joules represents energy. Example 2. An object of mass 40 kilograms is pulled across a horizontal surface by a force of 250 newtons. Here's my object. It is 40 kilograms and it is being pulled by 250 newtons. Acting at an angle of 30 degrees to the horizontal. The resultant displacement of the object is 20 meters, so this object moves 20 meters in that direction, and there's a frictional force of 30 newtons because it's moving along a rough horizontal surface. Draw a force diagram that shows all the forces acting on it. So let's draw a force diagram. We end up having our box, which has gravitational force acting on it. We end up having our frictional force acting on it. We end up having our normal force acting on it. And we have our applied force acting on it. Now, if we look at this, we know that our frictional force, let's add in the information that we know. We know that our frictional force is 30 newtons. We know that our applied force is 250 newtons. We know that our gravitational force is mass times gravity, which you can sit there and write as 40 kilograms times 9.8. And my normal is equal to my gravitational force. Okay, so here we end up sitting there and going to answer the questions. We've done number 1. Number 2, calculate the work done by each of the forces. Ignore method 1 and 2 for now. I will move on to that just now. But number 2 says calculate the work done for each of the forces. Well, there are 4 forces in this diagram, and out of those 4 forces, I need to calculate the work done by each of them. So we can calculate the work that is done by the applied force, which is FA times my change in distance times cos theta. Now, for my applied force, what is the angle between the horizontal, which is this line over here, and my applied force? Well, they gave it to me. It was 30 degrees. So I can go substitute these values in. It's 250 times the distance that it's moved, which is 20 meters, cos 30 degrees. If I plug that into my calculator, I get a positive 4,330 joules. That's my one work, according to my one force. The other work component was my frictional force. Now my frictional force times the change in distance times cos theta. If we look at this frictional force, we know that our item, our object, is moving to the right. But we know that our frictional force is moving to the left. Therefore, the angle between the direction of motion and the force that's being applied is 180 degrees. So if we go here, my frictional force is 30 newtons. Remember, it's an absolute positive value, so we only put that in. I know it's going in the opposite direction. Don't worry, the cos theta is going to deal with that. The distance is 20 meters, and we end up having cos 180. We know that 20 times 30 is 600, and we're going to times that by -1, which gives me minus 600 joules. That's how much work has been done, or negative work has been done against the box moving, basically, or how much work has been done against moving that box. Then we want to find out the work of our gravitational force, and our force over here, we can write it as F, little fg, delta d times cos theta. Now the angle in which, and remember we go in an anti-clockwise direction, the movement is in the right-hand direction. Our gravitational force is down. Therefore, the angle in which we're dealing with is 270 degrees. So if we go plug that in, we end up getting our force, which is the same as going mg times my distance times my cos 270. Now if you put that into a calculator, you'll see you'll get 0. Doesn't matter what I substitute into this place. Even if I substitute everything in, we're going to get 40 times 9.8 times the distance, which is 20 meters, and the angle ends up becoming 0. Anything multiplied by 0 is 0. And the same thing applies to the work that is being done by the normal force. We've got our normal force, that's our normal force, we're timesing it by the distance, timesing it by cos theta. Let's go see. Our normal ends up moving up that way. Our direction of our box moving is in that direction. The angle that that makes is 90 degrees. This whole item becomes 0 degrees. I don't even have to write it all out. All I can just say, it's not newtons. All I can just say is that it is 0 joules. Calculate the net work done. So number 3, how do I calculate the net of something? All I do is I add everything together. So the work of my applied force added to the work of my frictional force added to the work, that's not work, added to the work of my normal force added to the work of my gravitational force. If I had to substitute all the items that I've calculated so far, it's 4,330 joules for my applied force minus 600 joules for my frictional force added to 0 joules added to 0 joules, which gives me 3,730 joules of work that has been done to move this box a distance of 20 meters. Now, how is the net work affected if the angle between the applied force and the displacement is increased? It's an interesting question, and they normally ask these questions in the last part of your question banks. They'll ask you, state only if it's increasing, decreasing, or it remains the same. And then you've got to be able to decide what's going to happen to it. So if we look at this, let's draw our horizontal. This is our horizontal. And we know that currently we have an angle at 30 degrees to the normal, and its force is 250 newtons. I know that the more I push this up, if I had to draw my vector components for this, if I had to bring this down like that, I could draw this angle over there, and I could draw that angle over there. You can see the distance of it. But now let's, for instance, say I need to bring this item lower. It's still the same length. All I'm doing is bringing it lower. There, it's the same length. Do you see that? The only difference is now what's happened to this horizontal component. I'm going to make it a different color. It's gotten longer. Do you see that as we reduce this angle, this parallel force, vector or component, sorry, increases? And if that increases, that means I'm going to have a larger force being applied to this box, which means I'm going to have a greater work done. Okay, so how is the net work affected if the angle between the applied force and the displacement is decreased? If the angle decreases, the size of the applied force increases. Not difficult, eh? How does that affect the network? Well, the network, therefore, if the applied force is increased, it's directly proportional to the work being done. Therefore, the network will increase. That's will increase. Okay, I hope you understood that. That's a really nice question. Please ignore the method 1 and method 2. They've asked you separate questions specifically. Let's move on to the next section. Welcome to this lesson on the work-energy theorem. So, the work-energy theorem states that the change in kinetic energy of an object is equal to the net work done on it by a net force. Okay, we've just looked at net work in our previous example. Okay, we took all the different forces, we calculated the work done by each force, and we added it all together. We can simplify that process by looking at the net force first. We can calculate the net forces that exist within that system and then just multiply it. And that's where we get this equation from. The net work is equal to the net forces over the change in distance times cos theta. And we can change force into something like mass times acceleration. And if the force is in the same direction as the movement of the box, we know that that ends up becoming 1 because we substitute 0 degrees and then we get 1. So we end up getting mass times acceleration times the change in our distance, which is a very, very important equation, guys, if you need to remember it. And they've given you the mass, and they've given you acceleration, and they've given you the change in direction. You can calculate your net work, okay? Beyond that, they also told us that this net work, so the net work is equal to the change in kinetic energy. There's our kinetic energy, right? Okay. How did they do that? Well, we're going to look at it for the motion of this object. If we look at this motion of our object, we've got our initial velocity, we have a final velocity. We know that this object is going to move, and we know it's moving over a certain distance. So if we use our equations of motion, remember your equations of motion, one of your equations of motions is final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the change in distance. And if we rearrange this equation to get acceleration and change of distance as the subject of the formula, I move this initial velocity over first, it becomes a minus. Now I've got 2a delta x. I'm going to divide all of it by 2 basically, which means you end up all getting a half, right? You end up getting a half v squared final minus a half v squared initial. Now that kind of makes me think of my kinetic energy theorem, because my kinetic energy theorem ends up being half mv squared minus half mv squared. This is your final, that is your initial. And if I can take m out of that, I end up getting a half v final squared minus a half v initial squared. That's this equation over here. Okay. And what we noticed from this equation is that ax, which is this part over here, is equal to half final velocity squared minus half final initial velocity squared. All we're doing now is we're multiplying both sides by an m. That's all we're doing. So each side gets multiplied by an m, and then all of a sudden we get back to our network equation. So our network equation is equal to mass times this equation that we derive from equations of motion, which is your final kinetic energy minus your initial kinetic energy, which is the change in kinetic energy. The work energy theorem shows that the net work done on an object changes the kinetic energy of the object. And that's so logical, guys. Kinetic energy is moving energy. So let's take a box and put it here, and take a box and put it here. This is the same box as that. All I'm doing is I'm moving it a certain distance along. This is my initial box, and this is my final box. Okay? And what's happening here when I'm dealing with my initial box? Well, think about it. This initial box, the mass is still the same. The mass is still the same. The only thing that changes here is your initial velocity. We can have our initial velocity be faster or slower than our final velocity. It doesn't matter. But what ends up happening is that if this object is moving, it has kinetic energy. And if this object is moving, it has kinetic energy. And the change in this kinetic energy must therefore equal to the net work done on that system. I hope you understood that. Let's move on. So example 3 says, use the work-energy theorem to determine the speed of an object in example 2 after it has moved 20 meters. Assume that the object starts from rest and the net work done on the object over 20 meters is 3,730 joules. Now, example 2 was the example that we've moved that 40 kilogram object, so we've got 40 kilograms, and we've moved that 20 meters along with an applied force of 250 newtons at 30 newtons frictional force. We found out that the net work done is equal to 3,730 joules. Now they want us to use the work-energy theorem. Well, what is the work-energy theorem? The work-energy theorem is the net work is equal to the change in kinetic energy. We want to determine the speed of the object. So what is the speed of object? We need to assume that the object starts from rest. So my initial velocity is equal to 0 meters per second, and I want to know what my final velocity is going to be. So I substitute in the values that I need for change in kinetic energy, which ends up being half mass, and I can write this as final velocity squared minus initial velocity squared. Sorry, not on the outside. I wonder if I did that on the previous page. Just be careful. The square on the outside of the bracket means something completely different to the square on the inside of the bracket. For this, remember the squares are on each item. So just make sure I didn't make that mistake on the previous slide. So what do we end up doing? The mass doesn't change, it stays the same for both of these items. I can take a half out, it doesn't confuse me at all. What is my net work? Well, my net work is a positive 3,730 joules. And my mass is 40 kilograms. My final velocity squared is what I'm looking for. And I want to know how that change from a 0 meter squared is going to affect it. So this ends up being 20, so we're going to go 3730, divide that by 20, leaves you with final velocity minus 0, leaves you with final velocity squared. To get rid of the square, we square root both sides, and therefore my final velocity is equal to 13.66 meters per second. Guys, I took that straight from the textbook. I didn't plug that in my calculator. Plug that in your calculator and do the solution. Solve it and let me know what you get. But there you go. You found your final velocities, your final velocity motion of your box if it's being pulled by 250 newtons. Example 4. A trolley with a mass of 2 kilograms is initially at rest at the bottom of a runway. It is pulled up the runway, which is inclined uniformly at 25 degrees with the horizontal, by a constant force of 100 newtons. It travels a distance of 8 meters up the incline, and the trolley experiences a constant frictional force of 50 newtons. Determine the net work on the trolley. Guys, the nice thing about these questions is that you don't have to really worry too much about doing your components on your gravitational force here when you used to do it for your Newton's law, and I'm going to show you how if you keep all your forces separate, it makes your life a hell of a lot easier. And then it says determine the velocity of the trolley. Now, automatically we think net work, so we want to calculate net work here. And over here, determine the velocity. Well, velocity is in kinetic energy. And we know that our kinetic energy, the change in kinetic energy, is equal to my net work. So if I can find my net work from this previous question, I can then determine the velocity. For me to find my net work, I need to find all the separate work components. So now let's draw our force diagram, because that always helps us identify the forces that we are having to deal with. We have a force that is pulling up this trolley up the incline. So we call it our applied force, and they tell us it's 100 newtons. They also tell us that we're experiencing a resistance to going up the incline, which is, sorry, not 30 newtons in this instance, it's 50 newtons. So we're going to do double the amount of work to get it up this hill, right? Okay, actually a little bit more, because we also have our gravitational force. And this gravitational force has a parallel component pulling it down even more. So we're getting pulled down quite a lot. In this instance, normally what we would do to find our net forces is we'd do our vertical and horizontal components for this FG, but I'm going to show you how we can actually skip that whole process if we just do the individual forces and calculating the work done on each of the individual forces. Beyond that, we do have a normal force that we do have to take into consideration as well. Okay, so we've got 4 forces acting on this trolley. Let's go calculate the work done for the applied force. Now, we know that work is equal to the force times the change in distance times cos theta. My force that I'm pulling the trolley up the hill with is 100 newtons. It moves 8 meters. Now let's see, is the movement of my applied force in the direction of the object moving? Yes, it is, which means my theta is therefore equal to 0 degrees. And when my theta is equal to 0 degrees, my cos 0 degrees ends up giving you an answer of 1. So that ends up being 800 joules. Let's go calculate the work that is being done by my frictional force. So the work of my frictional force is equal to F frictional force times the change in X times my cos theta. Now, the frictional force is 50 units or 50 newtons. Remember, we don't need to put a negative there. This cos deals with that, the fact that it's going in the opposite direction. Okay, my change in my distance is 8 meters. And then my cos theta, let's go look at it. The distance is traveled is up the incline. The friction is working down the incline. So what is that angle between the two? Well, that angle, theta, is now 180 degrees. And when we take theta, 180 degrees, and we plug it into our calculator, we get -1. So this ends up being -400 joules. Now we want to calculate the work that is being done by my normal force. That's the easier one. Let's do that one first. Well, I don't know what force it is that is applying up there. I could calculate it, but it's unnecessary to do so. The reason being is that my cos theta is going to determine what's happening. And my cos theta, the angle between my normal force and the direction in which it's moving, is 90 degrees. And we know that if we do cos 90 degrees, that ends up becoming a 0 value. So we end up having everything times by 0, which gives me 0 joules. Now, my gravitational force. When I'm looking at my gravitational force, I need to figure out what angle it is that I need to adhere to. Now, if I'm moving, if my distance or my x is moving in that direction, and my gravitational force is down this way, I want to know what this angle is between the two. And the way that I can figure it out is that this line over here would be my 270 degrees, because I've rotated my axes so that it works along the incline. This is now my 0 degrees, this is now my 90 degrees, this is my 180 degrees. And because I've done that, this angle over here is always the angle between your perpendicular component and your force, which is 25 degrees, so that's 25 degrees. So if that's 270, and I need to minus 25 degrees from 270 to get this angle, I'm going to have 245 degrees. So in this case, where I'm looking at my gravitational force, let's all go back to black, times my change in distance, times my cos theta, and my theta in this instance is 245. All I do is plug that into this equation. My Fg, I don't know what it is, but I know that Fg is mass times gravity. My distance is 8, and it's cos 245 degrees. My mass for my trolley is 2. My gravity is 9.8. Times that by my distance and cos 245 degrees. And I get an answer of minus 66.27 joules. Okay, we had to find that angle that it makes, and this helps me figure that out. Now, have we solved for our net force yet? Before I erase everything, we want to calculate our net work. Well, if I add everything together, I'll be able to get my net work. So if I add 800 joules to a negative 400 joules to a 0 joules to a negative 66.27 joules, I'm going to get an answer of 333.73 joules. That is how much work I need to apply to this little trolley to pull it up the incline. The work has to overcome the frictional force. It has to overcome the parallel component of our gravitational force, and we end up pulling it all the way up. Okay, now it asks me, question 2 says that determine the velocity. Now, for me to be able to determine the velocity, we already discovered that I need to know my net work, because my net work is going to equal to my kinetic energy, and my kinetic energy has the velocity in it. So we're going to go net work is equal to half mass final velocity squared minus initial velocity squared. And my net work in this instance was 333.73, a half times my mass, which is 2. My final velocity is what we're trying to solve for. But do you remember what your initial velocity was? If we go look here, it says initially at rest. So my initial velocity was 0 meters per second. So we end up having 333.73. This ends up being 1, and I get final velocity squared. To get rid of that square, I have to square both sides, and I find out that my final velocity ends up being 18.27 meters per second. And which way is that? Well, it's going to be up the incline, because we took up as positive, hey? Everything that we've done, all the stuff going in the upwards direction is positive. So, guys, please calculate your work components separately, add them all together, get your net work. You'll save marks by doing it separately like this. If you do your net work together, if you calculate your net force, you guys mess that process up. So rather do it separately like this. And then determine the velocity of the trolley by square rooting both sides. I hope you've understood that. we are going to go on to conservative and non-conservative forces. Hey guys, okay, so sorry, I was busy messing around with my pens and drawing and stuff like that, but please can you complete Test Yourself 7, it's on page 154, and let me know if you get stuck on anything.